Hello, my name is Natsuko Kobayashi from Osaka University in Japan. Today I'd like to talk about liquid immersion technology, specifically for cooling network equipment. Immersion technology is exhibiting promising potential for high-efficient cooling for high-power servers. But hotspots in a data center are not only servers, but also core routers. Therefore, we examined whether this immersion technology can be applied to them as well, and found that it is actually as useful for communication equipment as for the servers. So first, let me give you a brief overview of the immersion technology, and then show you our experimental setting. Then I will talk about the most concerned aspect of liquid immersion, the telecommunication performance. I will go into the details of an optical and electrical evaluation of the effects of liquid immersion, followed by the results of its cooling performance. The immersion technology, as we have reported on various occasions, exhibits high performance in cooling high heat servers such as HPCI. And there are actually 4 ways to implement this technology, 3 of which are single-phase mode, using only refrigerant, and the 4th one is 2-phase mode using refrigerant and gas. And we employed one of the single-phase modes, the natural convection method, which requires no pump but instead uses the force of upward flow of refrigerant generated by the heat from CPU. And we also added the support of bubbles. As we reported last year here, with this method, high cooling characteristics were achieved while securing low PUE. And this is our experimental environment. 360 servers are implemented in 12 racks in the data center, which are connected by Cisco's 40 gigabit per second Immersed Leaf spine switches. And those switches we cool in a cooling tank using the bubble-assisted natural convection method. The heat density of this type of communication equipment is becoming extremely high, and eventually the equipment itself has become a hotspot in the data centers and communication machine rooms. Therefore, it's essential to cool them efficiently with immersion technology and power savings. The picture on the left is the actual leaf spine switch we used. First, from the back plane, we removed those large air fans and placed the switches in the cooling tank, like the picture on the right, along with 2 cooling plates connected to a heat exchanger. Here is a picture of mainboard, and the bubble injection nozzle is located underneath. And those bubbles assist the refrigerant to flow upwards through the mainboard, removing the heat from switch fabric and the CPU surface. Here on the right, you can see the bubbles reaching to the refrigerant surface. The biggest challenge of the liquid immersion cooling is securing communication performance of optical communication modules. So we examine them in 3 different settings, using a multi-mode module that is operated at 40 gigabit per second and 10 gigabit per second, and also a single mode module at 40 gigabit per second. And immediately we face a challenge. This graph shows communication performance of 40 gigabit per second module, and those lines indicate the fluctuation of the transmission reception power of the optical signal. It showed some link down and was unable to facilitate stable communication. This phenomenon was not observed with 10 gigabit per second module. To investigate the communication breakdown, we checked the optical flow of optical fibers connected to 40 gigabit per second module, placed in refrigerant and also in air. For this, we used OTDR analysis. And an almost identical OTDR trace was observed when immersed in refrigerant and when operated in air without immersion. This result indicates that the immersion of the module has no effect on optical coupling. How about the electrical characteristics of the refrigerant in high frequency range? More precisely, the effects of leakage of the high frequency electric field and also absorption of the leakage signal. These graphs show the change in impedance of 3 refrigerants over a wide frequency range up to 50 GHz. Here, light blue line corresponds to water, dark blue and pink correspond to fluoronet, and the yellow line corresponds to air for reference. Clearly, fluoronet shows a low dielectric constant, equivalent to that of air throughout the range up to 50 GHz. Those results indicate that the immersion technology has no problem optically and electrically. However, as I mentioned earlier, for some reason, 40 gigabit per second module showed communication breakdown. This inconsistency is under investigation, and detailed microscopic analysis is needed, including thorough examination of board materials. In order to solve the communication breakdown of 40 gigabit per second module, we applied synthetic rubber and polyimide to the electrical wiring surface of both single and multi-mode. Here are the graphs of the communication performance again. As we can see here, when the wiring was coated with synthetic rubber, link down was frequently observed and communication was not stable enough. On the other hand, when coated with polyimide, very stable communication was maintained. So as long as the wiring surface of 40 gigabit per second module is coated with polyimide, liquid immersion is effective with optical communication devices such as core switches and routers, as well as servers. In other words, servers and switches, which are the hotspots in the data centers and communication machine rooms, can all be immersed and cooled without intense air conditioning, resulting in dramatic energy savings. How much savings are we talking about here? Well, in terms of the power consumption of the leaf spine switch itself, compared to that when air cooling is applied, natural convection immersion and also bubble-assisted natural convection reduced by around 30%, simply due to the removal of all the fans in order to apply immersion. To maximize the power savings, we examine the optimal operating parameters when the leaf spine switch is immersed into a bubble-assisted natural convection system. And the DC motor was used for generating bubble flow. The graph on the left shows a change in the CPU package surface temperature with the bubble flow rate. As you can see, when the bubble flow rate increases, the CPU surface temperature monotonically decreases. In addition, simulation results in orange and experimental results in gray are qualitatively consistent, indicating that the simulation can be fully specified as a design tool. Let me clarify that the addition of a DC motor surely increases the total power consumption, but by an extremely small margin around 0.3 watts. So having a dramatic improvement in cooling performance, it's worth considering to utilize a motor for bubble assist. Last but not least, let me emphasize the bubble-assisted natural convection method achieved PUE of around 1.02, which is the same as the result obtained for servers. In this system, using the free cooling method for heat exchange keeps the contribution of heat exchange and bubble generation significantly low, of about 0.02. Therefore, by eliminating the need to air condition the entire data center, further reduction in power consumption can be expected. So far, I have demonstrated the effectiveness of liquid immersion technology. It exhibits high potential for cooling both servers and network equipment. Bubble-assisted natural convection method along with dielectric material coating of wiring surface enabled both sufficient cooling and communication stability at 40 gigabit per second. As a result, power consumption of switches were reduced by 30% while achieving PUE of 1.02. In conclusion, liquid immersion is a great alternative for air cooling and offers a promising solution to reduce power consumption of data centers, consequently making a positive contribution to sustainable society. Thank you.